Sorry about that. I forgot to turn him on. Let's let it do an audio check. Then I'll know whether. All right. Sounds like audio's on. Okay. These are the pictures from the three problems. Let me get the okay. So what he's done on this one, and okay, so this I probably should talk a few minutes about, but it really is not that uh, weird. What he's done is he's done this. He's done this equation. It's a little weird because generally speaking, okay, the density remains through the same throughout the whole problem here. So if you did this and you took a density and you multiplied it times everything, you would get P1 plus rho V1 squared over 2 plus gamma Z1 plus, equals to P2 plus rho V2 squared over 2 plus gamma Z2. This is more standard, but what he's written will work. This will work. It's a little bit odd. This is what mechanicals like more, and aerospace people like more. What civils like is they like to divide this entire equation by gamma, not by rho, but by gamma. And the reason being, hang on, is that, whoops, the reason civils like this, okay, so here's why mechanicals and aeros like this form. The units of this equation are pressure units, or pounds per square foot, or, newtons per meter squared, or, on the list goes on and on. Here, it's elevation, meaning it's in feet or meters. And why is that important? Why does civils like that more? The reason civils like this one more is because you can look at it and you can say, hey, that has 60 foot ahead right there. And that means this has 60 foot ahead. So that 60 foot's coming out here. So they can basically look at it. They can look at topology maps. They can look at, say, a mountain or a river or something. And if you're pulling water out of it, how high do you have to pump it up? Or how low is it going? So his first question is when the gate in D is completely open, there's your D right there. What's the water velocity coming out at C? So I'm going to pretend to be a civil here. I like civil engineering, actually, and it's kind of enjoyable. So what I've got is I've got 4 locations. I'm going to list them all. And what I'm going to list is the pressure, the elevation, and the velocity. And make my little table here. There's my nice little table. Okay, first of all, you can look at the elevation and figure things out real quick. First of all, he wrote the word datum there, so hey, I'm just going to go with that. 0, 0. Okay, A, 60. Come down to, that's going to be 52. Okay. Second thing, it dumps out in that atmosphere there. It dumps out, or not dumps out. There's a hole at the top so that it doesn't draw a vacuum, so you got that. Okay. Now, third thing. Think about this for a minute. And this is a common assumption. When the water is kind of flowing out of here, it is draining this tank. It is slowly, its level is slowly going down. But the velocity at A is really, really, really small. So then guess what happens if I square it? It pretty much can be neglected. So I can pretty much say that that's the case. So immediately you should recognize, that I know everything in that row. Okay, so this means anything that is unknown, I can turn around and I can write between here and here and find what goes in here. Once I have the velocity in the pipe at C, that'll be the same as the velocity in the pipe at B and at D if the pipe diameter never changed up through here. And if it does change, you can give me the diameters, and I should be able to tell you the velocity of that. So let's go about this. Okay, now the magic eraser. We'll copy this. We will copy this. And then what we're going to do is we're going to copy it again. And we're going to copy it again. Why? Because what I'm going to do first is go between A and C. Okay, so here's A, and what I'm going to do, see, I've already made a mistake there. That was supposed to be 2. So here's A to C. So, here's where my error was. That should have said 2, but I'm going to take all those off right now. I don't want to take that off. I want to take just the 2 and take that. We're good. Okay, so I'm going to come back and do those later. Okay. ZA, that's going to be 60. Velocity at A, that's going to be nothing. Pressure at A, that's going to be nothing. So on the left, you just get 60 feet of head. This is why civils love this. They just look at that and say, oh, I'm supplying 60 feet of head. That's simple. Then PC, okay, pressure at C, well, that's going to be equal to 0. Elevation at C, that's going to be 0. So the velocity at C squared over 2g. And so the velocity at C is going to be, well, this is the elevation or the head. 2g is going to be square root of 2gh, where that's 60, where this is in feet, so that's going to be 32.2. And then I'll give you velocity of C. Once you have velocity of C, if the pipe doesn't change in diameter, they're the same. Now, I can write something to ask myself, what's the pressure at D? Well, if I look at this, technically it's saying that this will be 0 in order for the energy to be the same here and here. Here, it's going to be different. So pressure is it's at 52, so the pressure is going to be a little bit different there. Because of this. Okay, now, okay, so the elevation, so what is it? B, pressure at B. Oh, yeah, that's what he wants to know. He didn't want to know the pressure at B eventually, so he does ask for that. Oops. See, can I do that? Okay, he wants to know pressure at B. Well, here's what I can do. B, B, B. Okay. So now I can do this. But I know from earlier when I found this that that's going to be the velocity at C, whatever that it happens to be. So in other words, I come down here and I have 60 is equal to pressure B over gamma plus velocity of B squared over 2g plus this times the z at B, which happens to be 52 feet because it's right here. So what I would do is I would take that 52, I would take whatever that velocity is and put it right in here. And the pressure at B would be gamma times 60 minus 52, which would be 8. And then I would want to take away this, move it to the other side, as well as move this to the other side. This would be VC squared over 2G. Why is it C? Well, because the pipe diameter remained the same, I think. Let me double check. It doesn't say it changed. So I do not see that the pipe changed in its diameter. So whatever the velocity had, you'd put it there, and you would basically subtract out 8 minus that, and then multiply times your gamma, and that would be your pressure. Now, could it be a vacuum? Yeah, it could be. I don't know whether it is or not. That is not that is not in the cards for me to know, but it very much could be a vacuum. Okay. So that took up too much space, so let's take this problem and move it down here. And then we'll take these other and move them. So I'll just work vertically down the page. So here we're looking at this one. Okay. Try to get that. Okay. So it flows through the thing at 10 meters per second. We want to calculate the whatever that is. That's a pressure gauge, by the way. So essentially, I believe he gives you this, but here, let's see. PA, we'll do it like a mechanical. PA plus rho. Well, usually gamma Z is listed first. But, you know, it really doesn't matter. Rho VA squared over 2 is equal to P2 plus gamma Z2 to B plus rho VB squared over 2. First of all, it stagnates right there. Stagnating straight on the tube. So, and what do I mean by stagnating? Let's zoom in on the tube. Here you got a pressure thing here. So fluid's coming and hitting this thing. Okay, so this is an impermeable object back here, so to speak. So it doesn't just keep flowing towards it unless you drilled a hole here and water spurting out here. So in fact, it's almost like it becomes a small wall of water, and the water kind of goes in and around it. But all inside this tube, the water is sitting dead still. It may be at a higher pressure, and it is at a higher pressure, but it's sitting dead still. So it's stagnant in there. The two elevations are the same or equal. So what you get is PA plus rho VA squared over 2 is equal to PB. So all you do is whatever he gave you for PA, you put that number in. This is water. Yeah, it's water. So it's 1,000 kilograms per meter to the cube for density. Velocity A, which in the picture, at least what I see, is 10 squared over 2 is equal to PB. So you simply add these all up, and that gives you your pressure at B. So it's just that simple. So let's see. Okay, let me, here, I'll tell you what, I'll do it this way. Okay, hello, 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 hello. Okay. I have no idea what's happening here. There we go. Excuse me, sorry. Okay. The other problems. So he's talking about the energy line or the hydraulic grade lines. And hang on, where is it? Okay. This is something that civil engineers aspire to, and it's okay. Again, if you write Bernoulli's equation like this, then everything is units of feet. So that means if you had water coming in and then going up to a reservoir and filling it up from below, let's say you had that, then essentially, eventually, what you would do is you would get to this elevation, which would be, say, 100 feet, or, 100 feet. But back here, maybe you're at, 3 feet high. So where's the other 97 feet? The other 97 feet have to exist at this point and at this point. Because you're at 3 feet back here. So in fact, you could find, and this is here, I'll try to draw this in a little bit better fashion. I'll try to draw it in a way somebody might draw it, a textbook. Here's your pipe. It goes way down, comes way back out. So if someone were to draw the water height, what they would draw is the elevation to, say, Z, and the elevation to, say, Z. But at this particular point, the velocity is pretty high. So what you would have here is you would have like a V squared over 2G, and then you would have the remaining would have to be the pressure. But if you're back here, say your elevation is moving slower, so you get this part being the V squared over 2G, and the pressure is much higher. So again, as you increase your velocity, you've decreased that pressure there. Eventually, you're here, and you're at Z. V would equal 0, and pressure would be equal 0 because it's sitting at the top. So you can change your pressure by shrinking the flow down and increasing its velocity, and then later on it slows down. If it slows down, the velocity head goes down, but your pressure head has to go up to compensate for that. And so, sorry. So the question here, now that we kind of see this, we're looking at the individual components of these things. Okay, hang on. Wait a minute. Okay, there's our components. Okay. He says pressure at hang on. Pressure at point A is equal to some number, and the velocity okay. The velocity is some number as well at A. The pipe diameter is down there. Then what happens is he wants to know the hydraulic head at that at that what am I trying to say? At that location. That's what I'm trying to say. First thing I think he's looking for is the information here. Since Z of A is equal to 0, okay, looking. Oh, he's giving you the pressure at A. So he has given you the pressure at A. Of course, you have that. So he gave that to you. Then the other terms that sat in here are those two terms. And that's pretty much it. But I don't, oh, I'm sorry. I do see that he did give the pressure there. So here, I was stumped because I thought he was not giving me the pressure. Okay. 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 So essentially, that's all it is. It's essentially the pressure that he gave me over gamma plus the elevation, but the elevation's 0, so that's basically it. Um, okay, then he wants to know the hydraulic head at the, which one? Oh, it's C. Um, so first of all, you've got to be able to take your velocity, which I'm looking to make sure he gave the velocity. And he does. Okay, so he gave the velocity back at A. And so what you're doing is going from A, A to PC over 2 plus ZC plus VC over 2. And so you move from there to here. And then what you're doing is, once you get that, he's looking for those two terms added together to give the hydraulic head. And he's got some sort of matching thing. Okay, so uh, so that's pretty much it there. Let's look at the next one. The next one is a water fountain looking, garden hose looking thing. And we'll put it at the bottom as well. Okay, so there you sit. So it says, gives you the two, all the information. It gives you the diameter, it gives you the other diameter. You can write, you have three particular locations, A, B, and C. A, B, and C. And in there you've got the pressure, the elevation, and the velocity. And if you just sort of recognize that the velocity at the very tip top is 0, pressure at the top, okay, let's see, that's nothing. Pressure here is nothing. We don't know. Do we know? We may not know this, so I'm going to take my datum here. Let's see. Does he have? Okay. He says a short distance. So exit. Yeah, I don't know. So in other words, I don't think we have that. We don't necessarily need it though. So elevation, B, nothing. C, 2. So immediately we recognize, we know all that. And so we know we can write this against that and find velocity at B. Then we can use continuity to work ourselves to the velocity at C. So basically I would say B over gamma plus ZB plus VB squared over 2G is equal to PC over gamma plus ZC plus VC squared over 2G. Okay, so we're looking at nothing, nothing, and 2. We are looking at no pressure, no elevation. And so what we're saying is VB squared over 2G is equal to the number 2. Or basically, you could say the height here of the water fountain. So guess what? Those are the same number, 2GH and square root. So the velocity at B is equal to this velocity coming out here at B is equal to square root of 2 G of 9.81 H of 2 meters and the square root of that. That tells you the velocity there. That may be determine the required water pressure at the pipe at A. Okay, now here you're gonna have to assume this is small since I don't think he gives it to us. I don't see it. And in that particular case, if it's small like that, then what you're doing is you're saying this. You're saying PA over gamma plus ZA plus VA squared over 2G. And you're going to assume the ZA is almost 0. So this is an assumption that isn't necessarily completely valid. But the key is, this would give you velocity at B, right? If you have the velocity at B, area at B times the velocity at B is equal to the area of A, velocity at A. Now, many people are used to seeing that. Basically, that means m dot in is equal to m dot out, but we don't need that. So if we had velocity of B, which basically came from right here, you can realize that the area ratio would give you this velocity A. And so what are you going to get for velocity A? You're going to get a little smaller than velocity of B. So in other words, if I look at these terms, look at that. Okay, velocity of B squared over 2G is equal to velocity of A squared over 2G plus PA over gamma. Since VA is going to be less than VB, you're going to move it over, and you're going to get some slightly larger pressure because gamma times VB squared minus VA squared over 2G equals to and that kind of leaves you where you are. And that's pretty much it. Okay, so we pretty much covered the three problems. Um, and the three problems had four specific individual problems in them. For some reason, he does that. Um, and we'll call it good for now.